It's my pleasure to present Assa Auerbach, because we started our studies together in Vaidman Institute, but both of us made only masters there, and I moved to Tel Aviv, and Assa moved to Stony Brook. After Stony Brook, he got a position in US in Boston, but decided to be a Zionist, and he's in Technion after Boston. And we'll talk about what are really electrons doing in solid state. Please.
Thank you very much. So, you probably recognize the people here on the right is Landau, Rude, Boltzmann, and Maxwell. These are just very, very few of the people who worried about the Hall effect during the years. And you can say, what could be new about something so old as the Hall effect? Turns out to be a very important tool for diagnostics of materials and for discovery of new particles in the solid state. I'll show you the theoretical problems related to actually understanding the Hall effect. Turns out that different systems, there are anomalies, things that cannot be explained simply by the simple theories. These are two anomalies I'll discuss. One of them is a divergence of the Hall resistivity in cuprates close to the Mott transition. The other one is the reversal of sign of the Hall effect in superconductors, completely separate systems. Actually, there are systems which exhibit both, but in principle, these are separate physical phenomena, but they share the fact that the Hall effect is telling us what is moving in a current. And one can ask, why is that a problem? High energy physicists have no problem identifying the charge of a particle by passing it through a magnetic field and seeing if it circulates clockwise or anti-clockwise and separating the positive and the negative particles. And the Hall effect is, in a sense, using the same force, but in more complicated situations than free particles. So a bit of history that I found, which is very amusing. Hall was a fellow in Johns Hopkins University. He wrote this very nice paper, starting with the saying that during the last university year, while he was reading Maxwell's Electricity and Magnetism, his attention was particularly attracted to the following passage, and this is something that Maxwell wrote. And Maxwell said, it must be carefully remembered that the mechanical force which urges a conductor carrying a current across the lines of a magnetic force acts not on the electrical current, but on the conductor which carries it. That was a statement by Maxwell, which Hall refuted in an experiment. In the end of the paper, what he essentially did, of course, is pass a current to a metal and found a transverse voltage, and he interpreted it as the effect was not reversed by taking the poles of the galvanometer from one end to this strip of the other. In short, the phenomena observed were just as we should expect if the electric current were pressed, but not moved toward one side of the conductor. In other words, he actually gave the current a physical meaning that Maxwell didn't. Maxwell thought the current, maybe it's like field lines, it's things that are mathematical to describe some field in space, but the physical things are the atoms and they are the ones who are supposed to feel forces. And in fact, the Hall effect is explained by, of course, forces on the electrons, which were not discovered at the time. But in fact, Maxwell was wrong, and Hall discovered his effect. So since then, as you can see, up to this point in time, the Hall effect.
Maxwell died the same year.
Okay. Yeah, I don't think he made many mistakes in his papers, but it goes to show the fact that you see some mistakes like that from historical figures shows that understanding of physics took really much longer than the time to write the equations down. And okay, so jumping now to these days, the Hall effect is of course used in very modern experiments. to discover exotic particles, for instance, fractional charge particles in the semiconductors, called the fractional quantum Hall effect. There are some recent Hall-like measurements. When I say Hall in general, it could be either thermal Hall or Hall, and also Nernst. The whole family of currents that are influenced by a magnetic field, one way or the other. And this is used, the thermal Hall effect in magnetic insulate used to claim that perhaps one sees Majorana edge modes in the ruthenium trichloride. Moti Haibum-Zuk, of course, uses it a lot to investigate the edge modes of fractional quantum Hall state. And recently in twisted bilayer graphene, there's been Hall effect measurements showing hysteretic behavior, showing some interesting phases that should be explored further. So in other words, it's a very timely subject. But we'll go now, rewind backwards to understand the basics of the Hall before we discuss more complicated stuff. And it comes to the current, because a metal carries a current. And the simple understanding of a current in band theory, as we teach in solid state 1, is that you have a band and you have filled electrons in the band. And the reason that a metal does not flow a spontaneous current is because you fill up the right momenta and the left momenta. Here it is. You fill these states and these states exactly the same way, and time reversal and parity ensures that for every k you have a minus k, and therefore you have the same velocities going in both directions. So overall, the electron system does not carry a current. That's the simple explanation. However, if you upset this occupation and you fill, let's say, one extra electron on the right, overall you'll have a current that is equal to the charge of electron times the velocity of that extra electron. All the rest cancel each other. That's one way to look at it. Another way to look at it is say, no, just a minute. I can look at these states that are empty as holes. And now notice that I have a hole here, an extra hole that is not above. All the other holes exactly cancel each other's current, but the current carried by this hole has a velocity going, of course, the opposite way as the electron. But if it's described by an opposite charge, you'll have the same current described in two different ways. Why do I plot this? Because this is a confusing issue. If the same current could be described either by electrons moving right or holes moving left, what is really carrying the current, electrons or holes? You think that there's no answer to that, but there is an answer. And the answer is the Hall effect can tell you whether what's moving are electrons and holes. And how does it do that? Well, same way as here, you can tell which is moving, the white pigeons or the black ones, which is flying and what is the background. It's the same question. But unlike in this picture, the Hall effect can actually give you an answer. So there's another piece of history, because this is a colloquium, I have to put some history. So I was pointed out by a friend in Paris that it's a very nice paper on history of solid state physics by Bain and collaborators. And there's a very nice thing about the Hall effect. So apparently Heisenberg was very interested in the Hall effect and in metals in general before he went to do a useless thing with nuclear energy. But what I say is that he gave Pyros his, I think he was a student, not a postdoc.
He doesn't look like a student.
No, that was old age. He gave him the problem of the Hall voltage. Why did he give him the problem? Because he said, look, the simple theory that I'll show you soon says that the Hall voltage should be essentially proportional to the density times the charge, and electrons are charged negatively, so the Hall effect should be negative. But this theory didn't work for many metals that had a positive Hall effect. And Pyros actually gave an answer to that, based essentially on the picture we showed before, that if one has a band which is more than half filled, think of it as a band of holes which have opposite charge, and now you have holes in the metal. And the holes are carrying the current, and that will give you a positive Hall effect. This was in 1929, before Dirac invented the holes in the Dirac sea. So Dirac independently thought that he could make the quantum mechanics relativistic for fermions, and for that he needed to have a full Fermi sea, which could have holes when you excite above the mass of the particle, and that those holes would act as positively charged particles called positrons. And what the paper says is that Bethe recently ascribed this omission, that nobody noticed that the holes were invented previously by parallels for solid state physics, because nobody believed that the Dirac holes were to be taken seriously until it was discovered in 1932. So this interesting part of history shows the confusion and the deep thinking that went into understanding currents. So how does it work? Well, this is a picture we show in elementary physics. We have this is a picture that has first applied a voltage called the Hall voltage, and the voltage is, just a second, is here. So you have a slope, you have particles with a charge, you have a magnetic field perpendicular, and you look at what happens, and what happens is a current flows by the electrons performing this cycloidic kind of motion and advancing at a particular velocity, which is dictated by essentially electromagnetism. The velocity is here, it's E over B times C. And if you plug it in, you get a whole conductivity of the density of charge divided by B. Now, what is more important is that if you invert this to get the whole resistivity and divide by the magnetic field, the whole coefficient, it's called, rho yx divided by B, is simply related to the charge density of the carriers, which has both the sign and the density of the particles that are involved in this current. Why is it more important? Because this is actually a result which is robust for systems that are not Galilean, in other words, completely translation invariant with no scattering, no potentials. So when you look at the theory made by Drude later on that has scattering, and it's taken from the theory of gases, this theory will give a much more complicated result for the conductivity sigma xx and also for the whole conductivity sigma xy. It's no longer equal to any C over B. But when you take this expression, which is sigma xy divided by sigma xx squared, to get RH, again, you get any C. So this is why the whole coefficient or resistivity serves as a characterization in semiconductors, in metals, in many systems of the carrier density and the sign. This result is actually a bit surprising because you're talking about the transport measurement, which is I versus V. It's a non-equilibrium or linear response, non-equilibrium dynamics, and nothing in the dynamics comes into the final result of the whole coefficient except the density, which is actually a thermodynamic quantity. It's an equilibrium quantity. Scattering rate, mass, all these things drop out from this expression. And one question that always bothered me was how general is that RH is independent of scattering rates, times, processes? And that actually gets an answer in this talk. It is quite general. This is beyond the approximations that go into the Drude theory. Okay. What is a good metal? For those of you not in condensed matter, of course, these are nice bands of electrons in K-space that are filled up to some Fermi level, giving you Fermi surfaces. And all the interesting transport for DC, for the low frequency, is around that Fermi surface in the limit of course, very weak scattering. So you have to have, if you want the distance between scatterers has to be much larger than the wave vector of the wavelength of the electrons at the Fermi surface. And this is a validity for both the band theory and for the transport, Boltzmann transport theory done on top of the band theory, and for Fermi liquid theory, essentially, which is a whole host of theories that are very well suited to describe metals with weak interactions and weak disorder. So, using the theory of Fermi liquid and Boltzmann theory, one can relate the whole coefficient and the whole sign to a geometric property of the Fermi surface, which is the curvature. And I'll give you a simple example which immediately shows what I mean by curvature. Think of a band structure of a square lattice, which looks like just circles with a diamond around them and circles here. So these are equi-energy contours. When you fill up the electrons below half filling, it has a positive curvature. It looks like closed circles, and the whole sign is negative because of the charge of the electrons. When you fill up more than half filling, it reverses sign, becomes positive, because now it's more natural to describe the band structure using circles of holes, which have the opposite charge. So that's how the lattice reverses the sign of the electrons. Essentially, through the interference of the Bloch waves with the lattice, you get both electron and hole type conductivities or hole conductivities depending on your filling. And this is a very important curve because this curve has two important features we have to remember. One of them is that the Hall coefficient diverges like 1 over density, both at the bottom of the band and the full band. But notice the full band is n equal to 2. 2 electrons per unit cell fills the band, not 1. At 1, we're half filling. This is exactly the diamond. There, in this particular model, the Hall coefficient vanishes. If you take the inverse, it looks like a divergence, but that's not anything physical. Just the Hall coefficient crosses 0 very nicely, smoothly. And there's no singularities in this curve anywhere except the two edges, here and here. So the important lesson is inside the band between 0 and 2, there should be no divergence of the Hall conductivity or Hall coefficient. But this theory seems to fail when you take metals with strong electron and electron interactions, and those require a different transport theory altogether than the Boltzmann theory and band theory that we discussed, and we'll talk about. So this is the known knowledge. You want to go to strongly correlated electron systems, there's a lot of challenges. The Boltzmann equation, being partly phenomenological because it has these scattering times in it, is really valid for nice quasi-particles, weak scattering. There is another formula, which I will show more of it here. It's called the Kubo formulas. These are very well-established linear response expressions that in principle could be computed for any model, strong interaction, weak interaction, any disorder. However, they have difficulties in computing them. They have intrinsic computational problems when you want to compute them. Finite size limitations, ill-posed analytic continuation when you do Monte Carlo simulations and quantum Monte Carlo simulations. And if you want to do evolution of operators, they have divergences at long time. In other words, they have problems that have not been resolved in most cases. And however, they are the ones that one should use.
Still rely on the fact that you are close to equilibrium.
Yes, linear response.
Linear response. So if you are off, then
right. But all my talk is about linear response. Things become even more complicated way, but in linear response, there's at least a very solid framework for calculating these coefficients, which are measured. Now, experimentally, if you want to know whether they're applicable, you just see if the response is linear of I versus V, and then you're safe using this formula. So this is highly technical. I just want to flash it a little bit. There's been some evolution in simplifying the Kubo formula, not approximating it, but just simplifying its calculations using a nice mathematics that might interest some of you, which is called the operator hyperspace. So it's an operator Hilbert space where the expressions for the conductivities are written in terms of, you want Green's functions of the Liouvillean. Liouvillean is the commutator of the Hamiltonian with any operator. The states of this Hilbert space are operators, like the current. And we are essentially elevating quantum mechanics to the level of operators and hyperoperators. And you might think that this is a useless mathematical complication, but it actually allows you much shorter routes to get to very useful approaches. Like
Kind of operator of state correspondence.
yes,
And I'm used to it in conformal field theories, but have it in any theory?
you can write a Hilbert space of operators if you define an inner product, which obeys the axioms of inner product, like hermeticity and Cauchy-Schwarz relation, and so on, and the norm, and that could be done by these expressions that I wrote here. I'm not explaining exactly what they mean, but they're essentially inner products between operators. One simple inner product one could use, which is not the one here, is trace of A dagger B is an inner product between A and B. You just write it in any basis, and you see that it obeys the usual relay. But this is using the thermal density matrix and so on. So not, I didn't mean it to. Sorry?
The derivatives, prime.
The prime is the imaginary part of the inverse of William. So you have at a minus I epsilon.
Between
This is
one
okay.
and 2 prime.
So okay, you write this operator as it's a hyperoperator. It's a commutator of the Hamiltonian with anything on the right, and you add to it a minus I epsilon, and then you take the imaginary part of the inverse. That's essentially a delta function of L, if you want, and this is the real part. What is interesting is that for the dissipative conductivity, you have the imaginary part, and for this, you have the real part, which makes this calculation more difficult. But again, I'll go back to it a bit later. There was a lot of work by our group and others using these expressions for continued fractions, expansions, which is a numerical way of calculating these coefficients. And what I did actually is expand the whole coefficient in terms of magnetic field, because each one of these operators depends on the magnetic field, like the currents do through the T minus EA, and the inner product and the Liouvillean and so on. But it's useful if you want to take the derivative of the whole coefficient with respect to magnetic field to start from here and end up with an expression which, again, won't tell you much, except that it relates the derivative of the whole coefficient, whole conductivity with magnetic field to the longitudinal conductivity squared times quantity, which is independent of any scattering mechanism and is actually an equilibrium quantity. So while this is not equilibrium, this depends on dissipation, and sigma xx, of course, depends on dissipation. This, which turns out to be the whole coefficient, because whole coefficient is defined by taking the ratio of the sigma dB divided by sigma xx squared. So this is actually an important result, that we get a computable summation formula for RH. It could be used now given a Hamiltonian, general Hamiltonian. And I'll show you the formula. But basically, the formula is this one. The whole coefficient is a ratio of two equilibrium susceptibilities. One is the current magnetization current susceptibility, written here. If you can write it as a commutator between three operators, but they're all local operators that could be, in many cases, even evaluated analytically. And the other one, the other susceptibility, is nothing but what's called the optical sum rule. It's the integral over the conductivity of all frequency. It's something that could be evaluated by taking a commutator of the polarization with the current. And there's a correction term. This expression here, of course, the first term is relatively easy to calculate because it's all just expectation values of not too many operators in the thermodynamic average. The second guy is more complicated, but as I'll argue, the second guy vanishes in case of disorder, and it scales with essentially the non-commuting part of the current with the Hamiltonian. So which essentially, if you have a system where the scatterings are not much larger than the Fermi energy or the characteristic energy scales of first term, the second term is smaller. Yes, question? You can get physical intuition in certain cases, like for instance, when you apply to the Boltzmann, to the band theory, and you cover exactly Boltzmann result. But for models that there's no other approach, this actually gives you the physical intuition. This is essentially, if you want to think about it, the magnetization is an operator, looks like R cross P. It's like angular momentum. It wants to rotate the currents, which is what the magnetic field is doing to the currents. I want to rotate the current and then evaluate its overlap with the other current. I wrote it as a commutator here, but it's actually an overlap also. Anyway, so without going too much in detail to this formula, which is a subject on itself, I just want to show applications to resolve some interesting questions of Hall anomalies that I showed before. Yeah. Yeah, okay. Well, this is a subtle question of definition. A transport like DC, current versus voltage, is non-equilibrium because voltage is not an equilibrium quantity. It's if you want a time-dependent gauge field, time-dependent. And getting a transport coefficient like conductivity, you need to put a time-dependent field and then take the frequency to zero last. This is the order of limits you have to take, even if you want DC. Because you say DC is nothing is moving. It's not true. You are, even in DC, experimentalists will tell you, even the most best DC experiments are usually done AC. You have to have something moving in order to move the current. However, so therefore you have like a dynamic problem. You have a scattering problem, you have a Fermi golden rule inside and so on. The magic of this formula is that the Hall coefficient doesn't care about that. The sigma XX cancels out. That's where all the dissipative scattering occurs. And the Hall coefficient, which is a ratio of sigma xy to sigma xx squared, is actually a thermodynamic quantity. You know, all these quantities, both the first and the second, are all given by quantities which are expectation values of equilibrium. Derivatives of free energy, if that's best to understand, okay? Not something dynamic. Yeah.
So the fact the claim is that it's independent of the strength of the interaction?
No, the interaction is in Hamiltonian. All the thermodynamic quantities like magnetization, density, anything that you measure in a system in equilibrium can contribute. But the expressions themselves, as they're written above, you see there are thermodynamic expectation values. They're essentially derivative of free energy with respect to a static time-independent source term. It's a completely different ballgame to calculate such a thing than a transport, because there's many, many ways of calculating thermodynamic averages. There's high temperature series expansions. There's Monte Carlo in imaginary time. There's variational methods. So most of us in solid physics like one system, one trick or another, but these are tricks that work well for statistical mechanical averages and not for transport. But fortunately, the Hall coefficient is actually in this class of problems. So let's see what we can do with it. Okay, so here I'm saying, yeah, there's other advantages of the formula. First of all, because of its way it's constructed, one can replace the Hamiltonian with a low energy renormalized Hamiltonian, which is not obvious from the Kubo formula. There you have a sum of all the eigenstates, and these expressions don't care about all the eigenstates, only the ones below the temperature. Second, you have thermodynamic averages, which are computable, as I said, high temperature series, Monte Carlo, also DMLG, people who know what it is. And you don't require to actually calculate real-time response functions. You don't have to do analytic continuation from imaginary to real-time, which is a big, big problem for DC limits. And you don't have to know scattering rates. And the second term, which is complicated, in many cases, not all, in many cases can be bounded or estimated by the model itself, by small parameters in the model itself. For instance, disorder.
By low energy, you mean relative to the Fermi energy?
No, relative to temperature. So if you're in a band situation, you really care about states close to the Fermi level. That's the low energy, I mean. Okay? It's a many-body low energy. By the way, there's two other formulas, one for the Nernst and one for the thermal Hall, that look very similar and have the same advantages, derived in a very analogous way, but I'm not going to discuss them here. Okay, so let's go to a system with strong electron-electron correlations that's been at the heart of attention of many of the theorists in condensed matter for a long time. It's the corporate high-TC superconductors. The reason they're so fascinating for theorists is because of the simplicity of the structure. The structure is a square lattice. It's kind of the simplest two-dimensional structure you can think of. The interactions are local and they're strong. And if you put 1 electron per copper, 1 electron per unit cell, actually, you will get an antiferromagnet because you'll just have 1 spin up, 1 spin down. There'll be a interaction, Heisenberg antiferromagnetic interaction, giving you an insulator with an odd number of electrons per unit cell, like 1. And it has a phase diagram that is well known, both for hole doped and for electron doped that go again contributed a lot to. This phase diagram in both sides of the. So what does the phase diagram mean? It says when you have 1 electron per site, you have this antiferromagnetic state. If you dope it with holes, it turns into a high-TC superconductor with D-wave symmetry. If you dope it with electrons by different compositions, you just change the other ions to give you an extra electron, you'll get the superconducting phase also. And this whole phase diagram kind of is not symmetric around n equal 1, but has some kind of a remnants of symmetry. At least if one wants to argue that you want to understand the superconductivity, it's nice to know that there's another superconductor on the other side. Now, this is a problem of strong interactions. Why? Because if you did not have strong interactions, then this will be a half-filled band. This will be actually the half-filled band I showed before, the square lattice with a diamond or maybe distorted diamond Fermi surface, very good metal, not an insulator. So the appearance of an insulator here is driven by the strong electron interactions called Mott transition. And probably closely related to the appearance of this Mott phase, which is driven by strong interactions, is the appearance of a very high temperature superconducting phase up to 100 and more degrees Kelvin, which is still under debate what is really the mechanism. But a lot of people agree that at least for the high energy physics, at least for this regime here of temperature, one can use the Hubbard model, which is a model that describes a square lattice with strong on-site interactions between the two spins. Now, I want to show that this actually is a system that gives you a Hall anomaly. What does it mean? If you look at the Hall coefficient in the electron doped, in a Hall doped case, sorry, and you dope away from half filling, then you get this decrease of a positive Hall coefficient. This is kind of old data by Takagi from many years ago, but it survives. And it appears quite high temperatures, much above the superconducting temperature and even above the Néel temperature. It seems to diverge, very strongly indicating at half filling. And that's an anomaly, as we said before, because Fermi liquid Boltzmann theory might explain the positive sign by distorting the Fermi surface with some extra interactions in the band structure. But it will never give you, at half filling, a divergence. And that's a strong indication that something is wrong, deeply wrong in any band theory that you want to use, even at high temperature. And one really has to understand this. Why is it diverging and what is the coefficient of divergence and so on? So how can you go about it if you don't have the Boltzmann theory? Then you have to look at the model. A model that can describe the physics of a hole moving around in an antiferromagnetic environment is called the TJ model. It contains two terms, but the most important is the first one. The first one looks like a hopping that you have in a simple band structure between site I and J. This is this hopping, but it's projected. This projection makes a big difference. First of all, it makes it a strongly interacting term in Hamiltonian. It has 1, 2, 3, 4, 5, 6 fermion operators. but it's a constrained hopping. It allows the electron to hop, let's say, from here to here, but it doesn't allow the electron to hop from here to here because it'll give you double occupation, which you have eliminated from your Hilbert space, arguing that this is a system of strong repulsion between the electrons. So if you use this model instead of the tight binding model, you have a very difficult, actually, many-body problem to solve. It's called the holes in the antiferromagnet. Occupied lots and lots of papers during the last 30 years. And this kind of holes in the antiferromagnet or antiferromagnetic fluctuations, which are spin a half, very strongly quantum, lots of singlet correlations in there, can give rise to quantum spin liquids, high temperature pairing. These are all statements people made without solid proof. I mean, only numerical evidence. But most important is definitely the idea of Bloch waves doesn't work here. You don't have really a single particle propagating freely, creating extended Bloch waves that you can fit. So what should we do? We can take this Hamiltonian and just plug it into the formula I showed you before, just to get the Hall coefficient. And that's what we did. And we didn't even do too much in terms of the phase diagram, except looked at high temperature limit to leading order, and now we're calculating the beta squared as well, and got an analytic expression for the Hall coefficient as a function of density. Definitely different than the 1/n behavior that you saw in the simple Drude-Boltzmann theory. And it does give you a divergence and a reflection of sign around half filling. The blue line is the Boltzmann theory or the non-interacting theory of the tight binding model. So you see there's a big, big difference between how the Hall coefficient behaves when you have the strong constraints of no double occupation. And this holds to high temperature relative to even the bandwidth of the electrons T. So the most important lesson is, first of all, there's a sign reversal here. You see, in the middle of a band, suddenly the electrons get squished and they feel the fact that there is a strong constraint and they change their sign. That's an effect we have to understand. And the second is a divergence that looks like this was the end of the band, which is not, it's a half-filled band. So relative to the Fermi liquid behavior, we have definitely a new phenomena. Some people call it Motness. It's a Hall sign reversal and divergence that is explained by this formula. Okay, so this formula, of course, is at high temperature, and one should always translate it to experiments by looking at the corrections in beta, and we're doing that. But qualitatively, it looks kind of similar to what was seen in experiment, and kind of rules out a lot of other theoretical attempts to explain these systems using band theory, even when they added lots of diagrams and vertex corrections and Fermi liquid corrections and whatever. The basis of the fact that you don't have a Fermi surface of the curvature that you started with is problematic in all these approaches. So, by the way, there were some numerical measurements in the Stanford group, which got qualitatively the similar results for the Hall coefficient.
The formula correct for n between 0 and 2?
Yes. But it reverses sign. So I think this is actually for n equal. Yeah, that's the positive sign. Yeah.
Electron delta to the left of the one?
So this is the left of the one. No, the left of the one is actually. No, this is the confusing thing about this. The data I showed before, okay. This was the Mott phase, and doping delta was actually in this direction. Okay? So you hold dope relative to half filling, but you're on the electron side of the transition. When you electron dope, you actually move to this direction. So it's very confusing. That's experimentally small.
This symmetric around n equals 1?
N equal 1 is the Mott phase, the middle.
This formula symmetric?
This formula is completely symmetric because the model is completely symmetric. Of course, not realistic for the real system, but qualitatively I think it gives you some understanding. By the way,
you have is not, does not look symmetric.
what?
The formula you have on the upper left.
No, the formula is for the, it just has to be inverted with a sign on the other side. As you can see, there's a discontinuity. This is the formula. So you just have to reflect it and also reflect it in sign. Sorry, yeah, I'll write it better next time. Okay, so this is an interesting. Now you want to understand why. That's a good question. Why does, first of all, the sign reverse and why they verge? And I show you a different system, which also have a sign reversal, which is not as studied or known, but it's a system that exists experimentally. It's a system of cold bosons, also on lattices, on optical lattices, described by what's called the Bose-Hubbard model. And if you go to low densities, you get the Galilean result, because at low densities, the bosons don't fill the lattice. They're essentially have a dispersion of p squared over 2m, and you can show that the Hall coefficient is just the Galilean's result. But close to half filling, if you're at a very strong interaction, in other words, two bosons do not want to be on the same side, so you have either 0 or 1, that's called the hardcore boson limit. You have a Hamiltonian of bosons hopping around with constraints that tell you that if you have two bosons at a certain site, the hopping will not be allowed. This description could be more easily represented using spin-half operators, which, as you can see, is just simply, oh, sorry, this should be Y. This is the XY model. This is the quantum XY model, spin-half, and it has transport, because it describes essentially these bosons moving on the lattice. If you want to think about it pictorially, then you can see that if you have like two bosons per side, then you have no hopping. But if you have 1 and 0, you can hop the bosons from the empty to the full, but you cannot hop it from the full to the full. Question is, for this system, which is partially filled bosons between 0 and 1, what is the Hall coefficient? And that's a calculation that was done in two ways and gave the following result. The first calculation, which was done using Chern numbers, which is a way to look at the ground state, exact ground state wave function, and calculate its Chern curvature and extract the Hall coefficient, was done by Netanel and myself and Dana Rovas, and then by Sebi Huber and Netanel, showed that there is a jump, and the Hall coefficient changes sign at half filling. So that reminds us a bit of this change of sign that we have in the fermion case in the TJ model. And this is a calculation using the new formula by my postdoc Sauri Bhattacharya, and we calculate the Hall coefficient formula. This applies now to the fluid state, which has a finite sigma xx and sigma xy, and it crosses 0 at half filling, changes sign between below half filling and above half filling. So unlike what you think bosons should do when you look at their Hall effect to be just giving you the density, suddenly in the middle of the filling, they decide to flip the sign of the carriers because of the interactions. So to summarize what we see both in the fermions and the bosons, I have this kind of a simplistic way of thinking about it based on a nice book I read. I don't know, a book about somebody was asking the question, I know the speed of light, but what is the speed of dark? Because when light moves and the darkness moves away from it, is it the same speed? Seems like a similar question, but if you have a current flowing to the right and you have a few particles in, as you can see in purple, and they're moving on a lattice, so you can only see them when they're on the lattice. So if they're moving to the right, you can see that they're moving to the right and the current is going to the right. So the particles are actually moving to the right and you have a current moving to the right. Now, if I occupy more than a half and I have the majority of the sites occupied, this is the case, more particles than holes. I'm doing exactly the same. The particles are moving to the right. But if you look at it, you see that, in fact, it looks like the holes are moving to the left. Because most of the particles can't move. And what happens is the current in this visualization is actually holes moving to the left. So this kind of a way of understanding this restriction coming from the fact you have hardcore interactions, that the current is actually carried by the minority because they can move more easily than the majority. So I don't know if this explanation is useful, but I thought it's nice to contemplate it because that's really the kind of hand-waving argument why the Mott phase wants to reverse the sign of the carriers close to it because it restricts the motion of the particle. How much time do I have?
Close to that.
Close to the end. Okay. The other part here is about the flux flow, superconductivity. And I just want to show that there is an argument for why sign is reversed when you think about what is moving in a current, which is the subject of this talk. This is the regime called flux flow, where you have a superconducting transition at some temperature here, and below it, you have a superconducting phase. But if you put a magnetic field, you will introduce vortices in the phase. So here you'll put a vortex lattice which doesn't move, and there's no transport. There's no voltages created on the system. But here, the vortices melt because of temperature and because of the density of vortices. And you can have flow and you can have resistivity. Then the question is, what is the Hall resistivity? And the Hall resistivity does funny things. So I won't discuss too much of superconductivity here. But what it does, it reverses the sign of the Hall coefficient when you cool below some temperature or when you reduce the magnetic field. This reversal of sign was a problem open for many, many years. This is a small example of many, many papers written on this Hall anomaly in the flux flow regime. So we looked at this problem, but we kind of did a different theory of flux flow, a different approach to the flux flow transport problem that is essentially based on having a vortex lattice, putting an electric field on it. You put an electric field on it. Of course, if the vortex lattice doesn't move, you have a short, and you get a burning of the lab. But there is a steady state that could be sustained in the system if the vortices move. Okay, sorry. Okay, so you see, if the vortices move, then the current doesn't increase linearly in time. And they have to move exactly at a certain speed. The speed is given by Josephson relation. It's E cross B divided by B squared. So the velocity of the vortex is completely independent of any material parameters in order to achieve the steady state. That's nice, because a lot of the other approaches that I showed before were calculating vortex dynamics and trying to find what is the velocities of the vortex based on a lot of phenomenological parameters. Here, because I'm applying a voltage and not a current, I can say exactly what the velocity is and eliminate the vortex dynamics problem, which was the problem of flux flow to begin with. Anyways, using that in this paper, we showed that the Hall conductivity is actually a sum of two terms. One of them was known, it's a sum of contribution of the cores. And another one, which is very nice, is just a simple charge, QV, carried by the vortex. We know exactly the velocity of the vortex. We know how many vortices there are because it's related to the magnetic field. So we can know exactly what is the conductivity due to vortex charge. And it's a very simple expression. It looks like the quantum Hall expression E squared over H, except here you have 2E charge of vortex. When you look at this expression, you ask, what is the charge of the vortex? Is it the charge of the condensate, which is all the stuff that's in the superconductor, or is it the charge missing from the vortex position? And here, the real nature of superfluidity comes in. There are two results in the literature. I won't mention the authors' names, but very strong group of authors said that what is moving is essentially the condensate density when the vortices are moving. They're dragging the condensate with them at the velocity that we know what they are. But this is an adiabatic argument. This is an argument saying that if I move slowly the Hamiltonian, all the wave functions and the condensate will move with it. That fails, breaks down in the superconducting phase and in the flux core phase, because in the superconducting phase, the superfluid is rigidly attached to the lab frame it was prepared at. And then when you put an electric field and the vortices move, the only thing that moves are these depletions. And they have the opposite sign of the charge carrier of the condensate. That's why you get their sign reversal in the hole. And that's essentially an argument why it works is because, okay, let me show it's a nice picture. So in a classical lake, you can roll because you can actually impart momentum and you can actually move around in a classical fluid using rowing. But in a superfluid, you cannot, because as long as you're not applying large enough force to create vortices, you have no essentially pressure and no momentum can be imparted into the superfluid. So the same argument will tell you that if you're moving slow enough, the potential, you cannot drag the full superfluid. You can only drag the vortices and their and that essentially gives you a value of about 1 electron per vortex per layer, which actually is a prediction that we hope somebody will look for in the experiment. And it's a general for many types of systems. Okay, so this I'll skip. Use that formula. So the take-home messages are that the Hall effect exposes the moving parts, and the sign reversal can occur for several reasons. One is spirals, holes. One is restricted hopping. One is wave function, superconducting wave function rigidity, which is related to vortex charge. And there are some new formulas that could be useful. And these are the anomalies I described. So thank you very much.
Just to see that I followed. You were all the time explaining the sign changing.
Yes.
But then there was the divergence.
You mean in the data?
In the, well, at least in the, also
This
in your
data.
models, I said.
Yeah, this data here is a sum of two terms.
What is the physics of the divergence?
Divergence. Near the mod phase?
Yes.
It's actually in the formula that I have there, the denominator vanishes.
No, not mathematics, physically.
Physically, it's the lack of carriers, because even in the simple classical way of understanding the Hall coefficient, it goes like 1 over n. The question is, where do you count n from? And it seems like you have to count n from half filling, not from 0. Why? Because at half filling, nothing can move. You see, there are particles there, but they can't move. So you're counting essentially the moving degrees of freedom, which is n minus 1. And the divergence is 1 over n minus 1.
Like electron holes.
No, because the bands are actually opposite. The below half filling, the bands are electron, above half filling holes. But this effect of the mod causes them two reversals, one at 50% holes and one at 75% electrons. You know what I'm saying? You saw the curve, right? Okay, I'm going to go left. Okay. Yeah. So you see there's two crossings here. On the left, this was supposed to be electron-like everywhere, so negative Hall coefficient, all the way to half filling. But already here, there's a crossing. And the crossing is exactly when the numerator here vanishes, which is around 0.454.
So why isn't it exactly at 0.5?
Because this expression is 8 and 16 and then 3. I don't know. These are numbers.
Okay.
Do you plot the formula as a function of n?
Yes.
But it does not diverge at n.
It diverges at any. Sorry. This is, as Amnon was asking, this is below half filling. So take this from 0 to 1, not from 0 to 2. Sorry. Yeah, those were asked already.
Can you explain please why others use the Cooper formula and
Why are they so difficult?
no, why they fail?
No, Cooper formulas don't fail. The calculations usually involve approximations, but nobody tried actually the Cooper formula on the TGM model as far as I know, because it's very computationally expensive. You have to diagonalize a very large system, all the spectrum, and they calculate all the matrix elements of the current in that spectrum. And it's exponentially large in the two-dimensional system. So it's actually impossible, even the biggest computers, to do the Cooper formula satisfactorily. But anyway, this formula allows, we calculated both the zero term and the correction term. We found the correction term was very small, it was around 1% of the first term. And that's the best we can do, but it's at least a new approach to get the Cooper, to get the whole coefficient. Yeah. Yes.
The formula you derive, correct at all temperatures?
No, this is high temperature limit.
This is the high temperature. So at the high temperature limit, it's actually very easy to do.
Not transport. You're right. If you want to calculate thermodynamics, Amnon will tell you how easy it is.
All the real calculations are at equilibrium.
Yes, but this is a transport coefficient that. No, you ask if it was difficult for us. For us, it was difficult because we're not experienced in high temperature expansions. But in general, high temperature series expansions are doable. I mean, up to order 7, 8, something like that. It becomes very complicated, lots of diagrams. But get the zeroth order is relatively easy, but the operators are complicated. So it's not the usual just magnetization or.
Yeah, the operators are complicated. The Monte Carlo is very easy.
Yes, so Devereaux did this for the Hubbard model, but he didn't do it for the TGM. And
what happens at zero temperature? Zero temperature, you can actually get everything from the imaginary temperature. You can get all conductivity from the.
Using my formula or using the Kubo?
Using not even Kubo, just using imaginary time Green function, get everything without analytical configuration.
Not transport, never. Transport is real-time evolution.
Yeah.
You cannot get it from imaginary time unless you analytically continue. And analytic continuation breaks down for DC because the limit for analytic continuation is beta omega has to be much larger than 1, which means temperature has to be lower than frequency. But DC is frequency goes to 0. So, and beta is the size of the system. So you always at the finite size system, if you take omega to 0, it breaks down. Now, some cases you're lucky and your result at finite frequency might resemble the 0 frequency, but it's not guaranteed.
Usually you can see the scale.
Okay, there are some cases you can make progress, but these are not metals usually.
Sure, maybe last question.
Yeah.
You calculate the Nernst coefficient, you get the constant for one superconductor.
I did calculate with this coefficient. That's something worth doing. Yeah. What?
You said that you can.
Yeah. The formula is allows to calculate now. But, okay, Nernst is very interesting, but also in the superconductor phase. What we can discuss.
Okay, so let's thank Assa again.